Mercedes-Benz automobiles, symbols of engineering excellence, are not only timeless in styling, but establish the standards for performance and state-of-the-art technology. Trends that have demanded peak engine performance while meeting stringent emission and fuel economy standards have brought about the continuous injection system with electronically controlled mixture correction, usually referred to as CIS-E. This Education for Excellence training program, CIS-E version, Operation and Diagnosis, will explore the fine details of this advanced version of the CIS fuel injection system. By the way, the information presented in this program relates specifically to the system as introduced on the 190E, but other models with CIS-E will be essentially the same, with, of course, certain differences to adapt to the engine type. It should be mentioned that we will not address the principles of operation of the continuous injection system, and it is necessary that you understand the standard CIS to fully benefit from this program. Therefore, if you are unfamiliar with the basic CIS, before proceeding, it is suggested that you review the following programs: CIS, Theory and Operation; CIS, Diagnosis and Adjustment; and Lambda System and Idle Speed Control System. To begin, it can be said in general that the important distinction of the CIS-E is that it is a refined version of the familiar CIS system, but with electronic sensors to provide more precise fuel delivery. Signals from these sensors are fed into an electronic control unit. The ECU is responsible for processing the information received from the sensors. The various sensors includes one for measuring the barometric pressure, one that transmits information on the movement of the airflow sensor plate during the warm-up period. Two switches are required to signal the position of the throttle plate. The micro switch signals idle position, and the throttle switch signals wide open throttle. A temperature sensor transmits a resistance dependent on the engine coolant temperature. An engine RPM signal is provided by the ignition module. And the oxygen sensor is utilized to provide information on the air-fuel ratio as indicated by the oxygen content of the exhaust gases. In addition to the signals provided by the sensors, the electronic control unit receives additional information during cranking and when the engine initially runs. A signal is also sent to the ECU when the air conditioning compressor engages. And finally, a signal is provided when the automatic transmission is engaged. Now that we have seen the various sensors and are familiar with the input signal that each provides, let's proceed with the next point of interest, and that is the question of how the resulting output signal is used to control fuel delivery. The output signal is transmitted to what must be considered the key component of the electronic control, the electro-hydraulic actuator, also called the EHA. As you can see, the EHA is mounted directly to the fuel distributor. It is a relatively simple device consisting of an electromagnetic coil which receives the output signal from the ECU. The coil surrounds a metal valve which can bend in response to the magnetism generated by the current flow. As shown in the illustration, fuel under pressure enters the EHA at the top and exits at the bottom. A calibrated return orifice ensures that a certain back pressure is always maintained in the lower chamber. The fuel returns pressureless to the fuel tank after exiting the return orifice. In effect, the EHA acts as a valve which controls the amount of pressure that will be allowed to pass into the lower chamber of the fuel distributor. The lower chamber pressure will directly influence the fuel delivery to the injection nozzles. The principle of controlling fuel delivery by regulating the pressure differential between upper and lower chamber is explained in the Education for Excellence program covering the lambda oxygen sensing system, so we will not repeat the explanation here. Depending on the direction of current flow and the intensity, the valve will bend towards or away from the fuel inlet orifice, thereby regulating the amount of pressure in the lower chamber of the fuel distributor. The resulting change in lower chamber pressure deflects the fuel distributor diaphragm, and more or less fuel is delivered to the engine as required. Let's review what we have just explained by taking a look at a specific example of what actually takes place. As explained, various sensors provide information to the ECU. In the example shown, a cold engine condition is being transmitted to the ECU by the engine coolant temperature sensor. The ECU processes the cold engine signal and adjusts the strength and direction of current flow to the EHA. The metal valve is deflected toward the inlet orifice. The incoming system pressure is thereby restricted. The restricted incoming pressure causes a drop in lower chamber pressure. The fuel distributor diaphragm deflects downward, and increased fuel delivery is provided to operate a cold engine at its optimum. The next example illustrates the conditions necessary to initiate fuel shutoff when decelerating. The first requirement is that the RPM signal transmitted by way of the TD terminal of the ignition system indicates a speed above 2,500 RPM. The second requirement is that the micro switch is providing a closed throttle signal. When these two conditions are met, the ECU transmits a strong current flow in the opposite direction. This results in the leaf valve moving completely away from the inlet orifice. Full system pressure enters the lower chamber, deflecting the fuel distributor diaphragm to the maximum upward position. Fuel delivery to the engine is completely shut off while coasting. As we have explained, fuel delivery to the engine is dependent on fuel pressure in the lower chamber of the fuel distributor, and it is the current flow to the EHA that regulates this fuel pressure. Therefore, to perform diagnosis, a fuel pressure gauge and a meter capable of reading milliamps are required. The pressure gauge is a Mercedes-Benz special tool, and two versions have been made available since the introduction of CIS. A multimeter of known quality, such as the Sun DMM5, is the second requirement. The fuel distributor has a test connection that is utilized for testing lower chamber pressure. The threaded plug is removed, and the hose fitting, marked either number 1 or A, depending on the version gauge set, is connected. The gauge connection, marked either number 2 or B, is connected to the fitting for the cold start valve. When the gauge is connected, the relationship of the system to the pressure gauge is as depicted in the illustration shown here. With the two-valve version gauge, if valve A is opened and B is closed, system pressure is connected to the gauge. And conversely, if valve B is opened and A is closed, lower chamber pressure is registered. With a single valve gauge, when the valve is closed, the system pressure circuit is blocked, and the gauge will register lower chamber pressure. When the valve is opened, although both pressures are connected to the gauge, system pressure is the higher of the two. Therefore, system pressure is registered. Testing current flow to the EHA requires an adapter cable, which is a special tool provided by Mercedes-Benz. The adapter cable is plugged into the EHA. The EHA connector is then plugged into the adapter cable. Returning to our illustration, it can be seen that the meter is connected in series with the EHA circuit and will indicate the current flow to the EHA. Before closing, the retention book that accompanies this program should be mentioned. It should be emphasized that the test procedures and specifications in this book are for the standard version 4-cylinder M102 engine, and only for model years 1984 through 1986. The 16-valve M102 engine, M102 engines beginning 1987, and 6- and 8-cylinder engines have many similarities, but there are important differences that invalidate some of the information found in the retention book. When testing the CIS-E system on these vehicles, refer to the pertinent introduction manual or service microfiche as it becomes available. This completes CIS-E version, Operation and Diagnosis. Another Education for Excellent Service training program.